Have you ever wondered what actually separates an infrastructure project that simply stands up from one that sustains the world around it? Well, let's dive right into this explainer. Today, we're doing something super practical. We are taking a dense 30-hour academic syllabus covering environment and sustainability, and we're transforming it into your modern, rigorous blueprint for the future. If you're designing, building, or managing literally any kind of project today, this is the absolute fundamental framework you need to operate successfully. So, can engineering actually save the planet? I know, it's a massive question. We usually think of environmental science purely in terms of conservation, right? Planting trees, river cleanups, that sort of thing. But in reality, it's a highly technical toolkit used to build and maintain the modern world. Planting a forest is fantastic, for sure, but engineering a zero-emission concrete mixture or designing a carbon-negative power grid, that is how technical professionals really move the needle. We're translating abstract ecological concepts into concrete, mathematically sound solutions. To figure out how we do that, we're going to move through 4 actionable phases: understanding Earth's fragile systems, the rules of sustainability, engineering sustainable solutions, and finally, assessing environmental impact. All right, let's kick things off with Section 1, Understanding Earth's Fragile Systems. Before we can design solutions, we really have to understand the physical canvas we're interacting with. Our Earth isn't just some static rock. It's a massive, kinetic engine made up of interconnected zones: the atmosphere, the hydrosphere, the lithosphere, and the biosphere. As a problem solver, you've got to realize every single project sits smack in the middle of these interconnected spheres. Imagine building a massive hydroelectric dam. You're altering the hydrosphere and lithosphere, right? But you might also trap vital, nutrient-rich silt. That downstream starvation degrades the biosphere, which then alters how much carbon local plants can pull from the atmosphere. It's like a giant puzzle. You're never designing in a vacuum.
But here's the thing, that natural baseline is taking a serious hit right now through pollution, deforestation, and habitat loss. For a builder, this represents the ultimate design flaw in our current global infrastructure. Think about a mountain highway project that just completely ignores local deforestation. Well, without the root systems from the biosphere to hold the soil together, a heavy rain in the hydrosphere causes a massive landslide, totally wiping out a $100 million road. Ignoring ecological blind spots directly causes catastrophic engineering failures.
Which brings us right to Section 2, the rules of sustainability. If the Earth's systems are the game board we're playing on, these are the rules we absolutely have to follow. Now, sustainability is one of those buzzwords thrown around a lot in corporate marketing, but its formal definition completely changes the math of any project. It's the practice of sustainable development and resource management across water, air, land, agriculture, and urban planning. It forces us to optimize everything. Building a water treatment plant isn't just about cleaning water once anymore. It's about optimizing urban and agricultural planning so that toxic runoff never even breaches the municipal supply to begin with. You have to treat resources as strictly finite variables in your equations. Designing these sustainable systems demands a profound shift in mindset. Looking at these program outcomes, problem analysis, the engineer in the world, and ethics, it really puts things into perspective. 50 years ago, an engineer's job was pretty much done if the bridge didn't collapse. Today, if that same bridge disrupts a critical wildlife migration corridor or relies on toxic anti-corrosion paints that leach into the groundwater, it's considered a total failure. Your scope of responsibility now encompasses the entire global footprint of the design. And because of that expanded responsibility, modern professionals must integrate these considerations into their daily workflow. You're navigating environmental laws, governance frameworks, corporate ethics. Imagine designing a multi-billion-dollar natural gas pipeline that has absolute perfect structural integrity. If that project fails to account for environmental justice laws impacting local watersheds, it won't just get some bad PR on Twitter, it will be permanently halted by federal injunctions. Legal and ethical compliance is literally as critical as tensile strength. Okay, moving on to Section 3, Engineering Sustainable Solutions. We know the baseline and we know the rules. Now let's open up the arsenal. We are aggressively shifting away from fossil fuels to renewable energy sources. We're talking solar, wind, hydro, biomass, and geothermal. But look, simply pointing a solar panel at the sun isn't engineering. The real technical hurdle is developing complex energy conversion technologies. It's the monumental task of engineering highly efficient chemical battery storage, upgrading our fragile century-old electrical grid to handle sudden surges of wind power, and creating smart infrastructure to route that energy exactly where it's needed in real time. The way we handle materials is also seeing a massive paradigm shift.
The old standard was a totally linear approach to solid waste management: collection, treatment, disposal. Basically, make it, use it, bury it. But the modern standard is governed by circular economy principles: source reduction, reuse, and repair. Think about a modern smartphone. Instead of gluing toxic batteries down so the whole thing eventually gets shredded in a landfill, a circular design uses modular components. You just unclip the battery, allowing those rare earth metals to be harvested and reused indefinitely.
And finally, we hit section 4, assessing environmental impact. You've got your design, you've picked your renewables, and you've planned for a circular economy. But before a single shovel even hits the dirt, every major infrastructure project undergoes an environmental impact assessment. This is a rigorous 5-step stress test. Step 1, screening, asks if an assessment is even legally required. Scoping draws the physical and time boundaries of the study. Impact assessment mathematically calculates the predicted damage. Mitigation forces you to alter your actual blueprints to minimize that damage. And finally, monitoring ensures the built project actually behaves exactly as promised for decades after it's finished. To execute those steps accurately, technical pros rely on highly precise tools, things like GIS, LCA, and risk assessment. Geographic information systems literally let you layer decades of flood zone and geological data right over your construction blueprints to avoid disaster. A life cycle assessment, it tracks the exact carbon footprint of a single steel I-beam from the second the iron ore is mined through the smelting furnace to the job site, all the way to its recycling 50 years later. It's rigorous, data-driven foresight. So it takes 30 total hours of intensive course instruction to really master these foundational principles. 30 hours of moving from the basic mechanics of Earth systems through complex international laws straight into high-tech mitigation strategies and circular economy design. Mastering this isn't just an academic exercise. Actually, it's more like the ultimate upgrade to a professional's operating system. It's exactly what separates someone who just pours concrete from a visionary who engineers self-healing, carbon-negative infrastructure. Because the environment isn't static, and neither is the technology we use to protect it. You are now equipped with the outline of this modern framework, combining ecological awareness with hardcore technical execution. You have the blueprint. So, looking at Program Outcome 11, Lifelong Learning, I'll leave you with this final question. How will you take agency, apply this toolkit to your next project, and actually engineer a truly sustainable future?